Hello there, Mr. Sutton here, bringing you the AB Calculus 611 Extra Practice Number 1 solutions on accumulation and rate in, rate out free response practice. On this free response problem, we have a pot of tea cooling, and the temperature is modeled by a differentiable function h between times 0 and 10, but they're not going to tell us what h looks like, except that they're going to give us a few values in this table here of h of t, but that's about it. So we're going to use the data in the table in this first part to approximate the rate at which the temperature changes at time 3.5. So we can't find the instantaneous rate of change of h at 3.5. We can't find h prime of 3.5 exactly, but we can approximate it by finding the average rate of change for the h function over an interval that contains 3.5. So taking a look at my table, probably the best interval to use here is going to be the interval from 2 to 5. Anything with 3.5 in it would work, but why not just use the closest one? So I'm going to do h of 5 minus h of 2 all over 5 minus 2. So that's going to be 50 minus 60 over 5 minus 2. So over 3. And let's see here. 50 minus 60, that's negative 8. So we have negative 8 thirds. And now the units here, since we've got degrees Celsius over minutes, that's going to be degrees Celsius per minute. For this part, they want us to use correct units and explain the meaning of 1/10 times the integral of 0 to 10 of h of t dt. And then we have to use a trapezoidal sum to approximate that with the table values. But let's start with the explanation. So whenever you have 1 over the interval length times the integral of a function, that's essentially the average value of the function over that interval. So specifically, this is going to be the average temperature, which we're going to measure in degrees Celsius, and that's going to be on the interval from 0 to 10 minutes. Now we have to actually estimate that using a trapezoidal sum. So I'm going to have that this integral is approximately equal to 1/10 times, and now I have a big parentheses with a whole bunch of trapezoid areas. Each trapezoid area, we're doing base 1 plus base 2 over 2 times a height. So the bases in this case are really these h values, and the heights are just the distances between the time values. So for our first trapezoid, we have a base of 66 plus a base of 60 divided by 2 times a height of 2. Next, we have 60 plus 52 over 2 times a height of 3. After that, 52 plus 44 over 2 times a height of 4 from 5 to 9. So you always have to pay attention to these interval lengths here. And then we have 44 plus 43 over 2 times a height of 1. So I could stick units on the end of this, and again, we already figured that out. That's going to be degrees Celsius. But I feel like simplifying it, and I'm allowed to use a calculator anyway. So here we go. So here we are. I entered this entire thing in my calculator using my fancy fraction mode. And pressing enter, we come out with this crazy looking fraction, which I'm now going to do math 2 on in order to convert that into a decimal. So that gives me 52.95 degrees Celsius. For this part, we need to evaluate the integral from 0 to 10 of h prime of t dt. Now you might be worried here because you're like, well, they barely gave me anything about h. They didn't give me anything about h prime. However, using the fundamental theorem, the antiderivative of h prime is just going to be h, and we're just evaluating that from 0 to 10. So basically, I just need to do h of 10 minus h of 0. Well, what is h of 10? That's right up here in the table. That's 43. And we're subtracting h of 0, which is 66. So that's going to be, let's see here, negative 23, and that's going to be in degrees Celsius. So what does this actually mean? Because that's another part of this question. Well, this represents the change in temperature. If you're taking the rate of change of temperature and integrating it, you're getting the total change in temperature. And this is the T's temperature because there's a biscuit later on in this problem. So I'll be specific here. Total change in the T's temperature in degrees Celsius from 0 to 10 minutes. For the last part of this problem, at time 0, we have some biscuits with a temperature of 100 degrees Celsius. Wow, that's like the boiling point there. They're removed from the oven. And the temperature of the biscuits at time t is modeled by this differentiable function b prime of t. Well, actually, it's modeled by b. b prime of t is the rate at which that temperature is changing. Using these models, at time 10, we want to know how much cooler the biscuits are than the t. Okay, so if I knew what their temperatures were, I could just take the biscuit temperature and subtract that from the t temperature, and that would give me my answer. So basically, h of 10 minus b of 10 is what I'm trying to find here. Well, the good news is I already know what h of 10 is. Looking at that in my table, that's just 43 degrees. B of 10 is going to take a little bit more work. So B of 10, we're going to have to use the fundamental theorem to figure out the temperature of the biscuits at 10 minutes. I'm going to have my initial value here, 100 degrees Celsius. And by the way, I'm going to subtract all of this stuff in a big parentheses. So minus parentheses, we've got 100 degrees Celsius, plus now I have to take the integral of b prime from 0 to 10. And let me just plug all that in my calculator. So to make things a little less bulky on the calculator, I'm actually taking my biscuit temperature change function, and I'm plugging that into y1 in my y equals. Now let me quit out of there. So I'm doing 43 minus, and now I'm going to open a parentheses. We've got 100 plus integral, so math 9. We're going from 0 to 10. And again, I'm basically taking 100 and I'm adding the total change in the temperature of the biscuits, which is hopefully a negative number. Hopefully these biscuits aren't getting hotter. So we need my biscuit temperature change formula. I put that in y1, so let me do alpha trace y1 there, and all the dx, and now let me just, that's dx I wanted, not df. So let me now close that parentheses and press enter and hope for the best. About 8.817, and that's going to be degrees Celsius. So this is how much cooler the biscuits are than the tea at time 10. On this problem, we have some grain being added to a silo. At time 0, the silo is empty, and the rate at which grain is being added is modeled by this differentiable function g that they didn't tell us a whole lot about, but they did give us a few table values for g between times 0 and 8. So first thing we have to do here is, using the data in the table, approximate g prime of 3. Well, since we can't find the exact value of g prime of 3, which is the instantaneous rate of change for g, we can at least find the average rate of change for g, and we're going to do this over an interval that has 3 on it. That will give us an approximation for g prime of 3. So that's going to be, let's see here, the interval 1 to 5 would work out pretty well. That has 3 contained in it. So I'm going to write g prime of 3 is approximately equal to, and now I'm going to do my average rate of change here. So g of 5 minus g of 1 over 5 minus 1. And again, note that I wrote approximately equals here. So that's going to be 20.5 minus 15.1 over 5 minus 1. And since you've got all constants, you don't have to simplify this. I'm going to, though. So plug in this into my calculator using my fancy fraction mode, alpha y equals there. That's going to be, let's see here, 1.35. So that's the actual number. Now, the units on this, we've got cubic feet per minute in the numerator. In the denominator, we just had the minutes. That's what we were doing down here. So that's going to be cubic feet per minute, or cubic feet per minute squared. So that's the actual units. Now, another part of this problem, they wanted us to interpret the meaning of g prime in the context of the problem. So this is going to be this is not the rate at which the grain is changing. This is actually the rate of the rate at which the grain is being added, not the rate itself, the rate of the rate. And this is, as we said, measured in cubic feet per minute squared. And this is happening at time 3 minutes. So you need every piece of this. You need what it is, the units, and also the time involved. For this part of the problem, we want an integral expression representing the total amount of grain added from time 0 to 8. Well, since the rate at which grain is being added is modeled by g of t, the total amount added would just be the integral from 0 to 8 of g of t dt. There we go. Don't forget your dt. And then to the next part of this, they want us to use a right Riemann sum with 4 subintervals indicated by the table to approximate this. So I'm going to write that this is approximately equal to the following. So I'm going to have 4 rectangle areas, each of a base times height kind of form. So I'm going to have, for the first rectangle, this is the one that goes from 0 to 1. I'm going to have a base of 1 times a height of, and now I have to pick between the left height and the right height. This is a right Riemann sum, so I'm always going to choose the right height for each rectangle. So we have a base of 1 times a height of 15.1. For the next rectangle, we have a base of 4 from 1 to 5 times a height of 20.5. After that, base of 1 times a height of 18.3. And finally, a base of 2 followed by, or multiplied by a height of 22.7. Now, again, as long as you stick units on the end of this, you don't have to simplify it. And the units in this case, since you're basically doing g of t, which is cubic feet per minute, times dt's units are minutes, you're essentially just getting rid of the minutes and just getting cubic feet of grain. You could put those units on. I'm going to simplify this, though, and then I'll put the units on. So carefully plugging all that in, I get a grand total of 160.8, and again, that's going to be cubic feet of grain. For part C, we've got some trouble here. The grain in the silo is spoiling, and that's happening at a rate modeled by this W of t function, which looks pretty gnarly. And this is measured also in cubic feet per minute, so it's kind of the evil counterpart to the rate at which the grain is being added, the g of t function. So using the result from part B, which going back to part B, we had 160.8 roughly cubic feet of grain that was added between times 0 and 8. So using that result, we want to approximate the amount of unspoiled grain remaining in the silo at time 8. So we basically have to take the amount that got added, which was again 160.8 approximately, and let me write approximately here. And now we have to subtract from this the amount of grain that's spoiled from time 0 to 8. Now to get that amount of grain spoiled, I mean this is the rate of spoilage here, the W function. I basically just have to take the integral of the W function from 0 to 8, and that'll give me the total amount of grain that's spoiled in that time. So I'm going to subtract then integral from 0 to 8 of Wt dt, and I'll do all of this on the calculator now because W of t is already defined up here, so this is all I have to show before the answer. Now, in order to do this efficiently on the calculator, I'm actually going to enter W of t in my y equals as y1. That way, if I have to retype this whole, I don't have to retype this whole thing if I want to use it again. So now let me quit out of there, and we are doing 160.8 minus, and now we're doing math 9 to get my integral from 0 to 8. And I'm going to do W of t dt in here, which on my calculator I need to do alpha trace y1 because that's where I stored W. And instead of dt, I'm doing dx because I always do dx on the calculator. Press enter, and that comes out to, takes a while for grain to spoil apparently, 61.749. And that's going to be in cubic feet. For the last part of this problem, based on our model in part C, so there was that W of t function from part C, we want the amount of unspoiled grain in the silo. We want to know if it was increasing or decreasing at time 6. So let's write a function for the rate of change of the amount of unspoiled grain. That's going to be the amount of the rate at which grain is being added, g of t, minus the rate at which it is spoiling, w of t. So g of t minus w of t is my rate of change in unspoiled grain. And again, w, that was defined back in part C. So now if I want to figure out whether this, the amount of unspoiled grain is increasing or decreasing at time 6, I basically need to know whether this quantity, when I plug 6 into it, g of 6 minus w of 6, I need to know whether that's positive or negative. So I can just do that directly on the calculator. So first let me do g of 6. Now g is defined in this table. G of 6 is just 18.3. So let me just plug that in. And for that, I'm going to subtract. I need to do w of 6. Recall on part C that I stored w as my y1 and y equals. So I'll just do alpha trace y1, open a parentheses and plug in 6, and press enter. That comes out to 2.237, roughly. So since this is a positive quantity, this tells me that the amount of unspoiled grain is actually increasing at time 6. On this no calculator problem, for 0 to 6 seconds, a screensaver on a computer screen shows 2 circles that start as dots and expand outward. Sounds like a blast to watch there. At the instant, so this is the first task here, at the instant that the first circle has a radius of 9 centimeters, the radius is increasing at a rate of 3/2 centimeters per second. Okay. We want to find the rate at which the area of the circle is changing at that instant with units of measure. So we're looking for a rate of change. We've already got one rate of change for the radius. We want the rate of change for the area. This is a related rates problem. We have to begin by writing a formula that ties everything together and then differentiate that implicitly with respect to time. So since we're talking about area of a circle, how about we write the area formula for a circle? A equals pi r squared. Now I'm going to take the derivative of all of this, treating every variable as a function of time. So the derivative of a, that's going to be dA over dt. And derivative of pi r squared, that's going to be 2 pi r times a tail of dr over dt. So everything is an inner function of time. So what did they give us here? Well, they wanted us to find dA over dt. That was the rate of change of the area. And they gave us the radius, which they said was 9. So we can plug 9 in for r right there. And dr over dt, that's the rate at which the radius was changing. Since the radius is increasing at a rate of 3/2, this is going to be positive 3/2 over here. And now we just need to multiply this out. We can leave it in terms of pi. We just need to make sure that we put units on it. So you actually don't need to simplify the number part of this, but if you wanted to, these 2's are going to cancel. So you basically have pi times 9 times 3, which is 27 pi. And for the units, well, we have area over time. Since the one-dimensional unit is centimeters here, the area units is going to be centimeters squared. The time units, they told us, is seconds. So this is going to be 27 pi centimeters squared per second. For the second part of this problem, we're told that the radius of the first circle is modeled by this w of t function. And we want to know at what time is the radius of the circle increasing at a rate of 3 centimeters per second. So in order to solve this, we basically need to figure out what w prime looks like. We need the rate of change of the radius of the first circle. And then we just need to set that equal to 3. So w of prime, let's see here, 12 is a constant, so that's just going to be 0. And for this exponential term, I'm going to have negative 12e to the negative 0.5t times the inner derivative using the chain rule here of negative 0.5. Negative 0.5 times negative 12 is just going to give us 6. So we have 6e to the negative 0.5t. That's w prime. And we wanted to know when this equals 3. Well, to solve for this, we can start by dividing both sides by 6. So we have e to the 0.5t equals 1/2. And then after that, to get to t, we have to get rid of this e here. So we take the ln of both sides. So I can write negative 0.5t equals ln of 1/2. And then finally, to get t, we'll just divide by negative 0.5. So t then is going to be ln of 1/2 over negative 0.5, and that's going to be in units of seconds. Now, if you wanted to, you could simplify this a little further. I'm not going to, but if you wanted to, you could pop this negative in as an exponent, and this is really ln of 2 divided by 1/2, which would all simplify to 2 ln of 2. But who's keeping track? For the final boss battle on this free response, we have a model for the radius of the second circle given by f. F of t, we don't know the exact function, but we do know f prime of t they're giving us. It's t squared minus 4t plus 4. Based on the model, how many centimeters does the radius of the second circle increase from time 0 to time 3? Well, we have the rate at which that circle's radius is increasing. To find the total amount of increase, we just have to integrate f prime over the interval from 0 to 3. So I'm going to write integral from 0 to 3 of f prime of t dt. And I don't know what the f function is, but I can at least take the antiderivative of f prime. So that's going to be, using my reverse power rule, we're going to have 1/3 t cubed minus, let's see, this bumps up to 2. Dividing by that, we have minus 2t squared plus 4t. And we're evaluating all of that from 0 to 3. So I have all of this stuff with 3 plugged in, minus all of this stuff with 0 plugged in. You actually don't have to simplify this. You could actually just stick the unit of centimeters on the end and call it a day, since this is all constants. But if you wanted to, all these terms with 0 are going to cancel out. And then over here on the left bracket, we have 1/3 of 27, which is 9. We're subtracting, let's see here, this is 2 times 9. So we're doing 9 minus 18, which is negative 9. And this is now going to be, we're going to have negative 9 plus 12, which gives us a grand total of 3 centimeters. That is how many centimeters the radius of the second circle increases from time 0 to time 3.